Here we have the square root of 5 times the square root of 15. Now, I suggest we do this kind of work the following way, using prime factorization. So the square root of 5 times the square root of 15 can be rewritten as the square root of 5 times the square root of 5 times 3. And then the product rule for radicals allows me to rewrite this as 5, the square root of 5 times 3. So this is the square root of 25 times 3, right? And so the square root of 25 is just 5, and of course the square root of 3 is the square root of 3. So this is a way of using prime factorization. For this one, which says 5 root 8 times 7 root 3, we're going to want to multiply the 5 and the 7 to give us 35. And then we're going to want to multiply square root of 8 times the square root of 3. Okay, everybody? So then this turns out to be 35, and then we have the square root of 8 times 3. Now, I suggest we write that as using prime factorization. 8 is 2 times 2 times 2, and then just bring down the 3. Remember that your index is 2, because this is a square root. So let's group these in factors in a group of 2 like that. So really, this turns out to be 35 times the square root of 4, right? Times the square root of 6. This is the square root of 4. This is the square root of 6. So 35 times 2 root 6 gives us our final answer of 70 root 6. I think this method of, or this approach of multiplying radical expressions is extremely valuable, especially here in this example. So I suggest you rewrite this as, instead of 25x, rewrite it as 5 times x times the cube root of 15x squared, rewrite that as 5 times 3 times x. So really this turns out to be the cube root of, now we know, but the product rule allows us to rewrite this as 5 times 5 times 5, and then there's a 3. Of course, x times x times x. So really this is 3 times, now let's not forget, your index is 3, so you want to group these 3 5s together and these 3 x's together. So really, there's a 5 that's on the outside of the radical. There's also an x on the outside of the radical. And the only thing that remains is the cube root of 3. So your final answer is just 15x times the cube root of 3. In my opinion, that was probably the best way to do this kind of problem here. Because if you would have multiplied straight across, 25 times 15 is pretty large, and then you would have to simplify that large number. So I like prime factorization. All right, so we have a new problem here. Now, what I notice is that the expression inside cannot be simplified. These are not like radicals, right? And the reason why they're not like radicals is because the radicands are different. The indices are the same. Actually, the indices across the board are the same. Square root, square root, square root. So the indices are 2. But these radicands are different. 14 and 21 are different, so you cannot combine these two. Furthermore, 14 does not have a perfect square as a factor, neither does 21, so they cannot be simplified. So then I feel led to distribute the number on the outside. So what we're going to do is we're going to multiply 2 times 4, and that'll give us 8. Okay, and then I'm going to rewrite this as the square root of 7 times the square root of 14. 7 times, and then 7 times 2, all right? 14 is 7 times 2. Minus, and then here we go. 2 times 5 is 10. Like this. And then 7 times 21, right, is what? 147, but I'm not going to write it that way. I'm going to write it as 7 times 21 as 7 times 3. Okay, everybody? Now, your index, don't forget, is 2, So that's a group and that's a group. So really this turns out to be 8, 8 times 7 times the square root of 2 minus 10 times 7 times the square root of 3. 56 root 2 minus 70 root 3. Now we can't go any further here because everything is simplified and they're not like radicals. All right, next we have the square root of 11 minus 3 times the square root of 2 times 4 root 11 minus the square root of 2. All right, so what we should do here is distribute square root of 11 times the first term, then the square root of 11 times the second term, like that. Let's get that first, okay, everybody, and then we'll continue. All right, here we go. So we have 1, which is, I'm not pointing at the index is 2, okay? I'm pointing at the coefficient that's in front. A positive 1 times 4 is 4. And then the square root of 11 times the square root of 11 is the square root of 11 times 11, like that. Minus, now this is 1 times 1, which is 1, and then 11 times 2, which is 22, okay? Next, I will distribute this term to both of those, okay? So here we go. We have negative 3 times 4. That's negative 12. And then we have the square root of 2 times the square root of 11. That's again the square root of 22. Finally, we have negative 3 root 2 times negative root 2. So first of all, this is going to be a positive. And then we have, let me see if I could fit it there. We got 3 times that invisible 1, so that's 3. And then we have the square root of 2 times 2. So it'll be 2 times 2, like that. All right, everybody. This is basically 4 times the square root of 121. Notice here that these are actually like radicals. We can combine these two. Remember how to combine them. You keep the like part the same, which is the root 22, and you add the coefficients. So negative 1 minus 12, or plus negative 12 is negative 13. So I'll do negative 13 root 22 plus 3 times the square root of 4. So then this is 4 times 11, because the square root of 121 is 11, minus 13 root 22 plus 3 times 2, because the square root of 4 is 2. So 44 minus 13 root 22 plus 6. We're just about done. It's just that the last term and the first term are like terms, so we can combine those to make 50 minus 13 root 22. So this is the final answer. All right, here they're asking us to find the square root of 13 squared. Now, I want to talk a little bit about this. So the square root of 13 squared means the square root of 13 times the square root of 13. And by the product rule for radicals, we have the square root of 13 times 13, which is just the square root of 169, which is 13. So the final answer is just 13. So what I would like to do is just emphasize that the squaring action cancels the square root action. So we can go from here all the way to the final answer without having to go through all of this. So we can skip this if we understand that the squaring action is the inverse operation of the square root action. All right, we have 4 times the cube root of 2x squared, quantity cubed. Now we're going to have to cube everything that's inside of these parentheses. Cube everything that's inside the parentheses. So in other words, we're going to have to cube 4, and we have to cube this cube root, like that. All right, 4 cubed is 64, and then here we go. The cubing action cancels the cube root action, so you're just left with 2x squared. So 64 times 2 is 128, and then x squared is the answer. Now the next example here is very important, so please pay close attention to this. The square root of 7 plus 3, quantity squared. What I've seen a lot of students do, which would be the wrong move, is they distribute this exponent. And so I've seen students say, well, I need to square the square root of 7, and I need to square 3. So then I get 7, right? Plus 9, so my answer is 16, which is incorrect. We never, ever distribute exponents across addition or subtraction. All right, so let me redo this problem the correct way. Now remember your answer, this wrong way, remember the answer was 16, okay? And that's the wrong answer, but remember that number 16. And let me show you the correct way to interpret this problem. We know by definition that exponentiation means repeated multiplication, right? So that exponent of 2 really means the square root of 7 plus 3 times the square root of 7 plus 3, right? That's what the exponent means. Now, if I distribute this, right, like this, and then do this distribution as well, notice what we get. Let's see, the square root of 7 times the square root of 7 is just 7, and then the square root of 7 times 3 is 3 root 7, and then here 3 times root 7 is another 3 root 7, and then finally 3 times 3 is 9. We can add the 7 and the 9, right, together, the 7 in the front and the 9 on the back end to get, watch this, 16. But that's not all we get. These two terms are like radicals, so we can combine them by adding 3 plus 3, which is 6, and keeping the like radical part. This is the final answer. So this is much more than just 16. This is 16 plus 6 root 7. So please remember that we never distribute an exponent across addition or subtraction.